Now let's see how the system we looked at in the last clip, for which we've applied a force with an angular frequency omega 1 to an oscillatory system that has a natural frequency of omega naught, giving us the following solution, or the solution indicated here, the homogeneous solution plus the particular solution. Okay, we want to think about what this particular solution tells us about the way the system is going to behave. And one way to get into that is to simply consider what happens if we have a certain set of initial conditions. Now, your textbook, in its current version, assumes initial conditions x naught equals 0 and x prime at 0 equals 0. And that corresponds to the pendulum initially stationary. And I start applying whatever force I apply, and the pendulum starts moving in response to that force. I'm going to use a different set of initial conditions. I'm going to assume the pendulum is initially at its equilibrium position, but that it's given some sort of initial velocity at the same time the force begins to apply itself. So the initial condition will be x of 0 equals 0, the object initially at its equilibrium position. X prime of 0 equals v sub 0, where v sub 0 is just some initial velocity. And we're going to assume that this occurs at the same time the force begins to be applied. Now, it's very easy to apply these initial conditions mathematically, algebraically, to the given solution. X of 0 is what we get if we plug 0 into this equation. And if we plug in 0, we're going to have a cosine of 0 here and a cosine of 0 here, and the sine of 0 here. Well, the sine of 0 is 0, so the C1 term isn't going to appear at all. The cosine of 0 is 1, so we're going to have just the C2. That's going to appear here. And the cosine of 0 here is also 1. So that we're going to have just the f over m times omega naught squared minus omega 1 squared, which I've written here. And that has to equal 0, since the initial position is 0. So we easily solve this condition to find that C2 is just going to be the negative of the f over m times omega naught squared minus omega 1 squared. Now, x prime of 0, well, x prime, our sine is going to become omega naught times a cosine. Our cosines are going to become omega naughts times negative sines, and omega 1 times a negative sine. But both of these are going to have sine functions as their derivatives, and the sine of 0 being 0, they don't affect the initial condition at t equals 0. This one does affect the initial condition on x prime. The derivative is going to be omega naught times the cosine of omega naught t. T is equal to 0, so the cosine is going to be 1, so we're just going to end up with an omega naught times C1. So x prime of 0 is omega naught times C1, that equals V0. So it follows that C1 is V0 over omega naught. And it's then straightforward to substitute C1 here in our original solution and C2 here in our original solution, and simplify the solution, which will come out in the following form: x of t equals this. I'm not going to read these to you. You can substitute these parameters into the equation and see that everything simplifies into this form. Now, before we proceed any further, let's just think about the effect of omega naught and omega 1. If omega 1 is close to omega naught, then this C2 is going to be very large because this is going to be very small. The closer omega 1 is to omega naught, the bigger the value of C2. And of course, C2 affects this term of the solution. Omega naught being close to omega 1 has the same effect on the coefficient of the cosine of omega 1t, so that when omega naught and omega 1 are close, this term becomes very large, and this term having the magnitude V naught over omega naught, maximum magnitude V naught over omega naught, remains the same no matter how close omega 1 is to omega naught. So that as omega 1 gets close to omega naught, this term becomes much larger while this term isn't affected. So this is just a sine oscillation with an amplitude of V naught over omega naught. Okay, this is something different, and this coefficient, we'll see how these things combine, but this coefficient becomes large as omega 1 becomes close to omega naught. We then conjecture that if omega 1 isn't close to omega naught, this denominator is going to tend to be larger, and this term isn't going to be as significant, so that we just have a simple sine oscillation. However, if omega naught is close to omega 1, this term becomes more important, and we'll see how that works out. Now let's consider the behavior of this term here, cosine of omega naught t plus the cosine of omega 1 t. Now I'm going to digress just briefly, hopefully briefly. There are equations that you should have learned in a trigonometry course or in a pre-calculus course that contain trigonometry that allow you to combine these two terms, but nobody particularly remembers them, and people at this point in 2013 seem to think that it's not important to remember them because we can always Google them. To some extent that might or might not be true, but I will express the opinion that if you don't hold some stuff in your head, if you've got to find everything every time you need it, then you're limited in your ability to think about things, and it's the people who know how to think about things that are going to dominate their professions. So you might want to just kind of store that away.